Oh, hi. Welcome to part two of chapter two. We will start from section 2.5, the periodic table. And first, let me share the screen, all right, so that you can see the whiteboard along with the PowerPoint slides. On my right is the whiteboard, and of course the on the left PowerPoint slides. I'll be toggling between the online or going to online to show you some of the items I would like to share with you. First of all, what is a periodic table? We all know periodic table is the systematic organization of elements. You have seen the periodic table before. I've shown you in the previous lecture session on what periodic table is all about. But the question is, how did we end up with the periodic table? In early 17th century, there were only few known elements, and at that time, it wasn't really hard to keep track or to memorize the chemical properties and the physical properties of those few known elements. However, in the late 17th century, early 18th century, there was a remarkable discovery of so many elements, and scientists were struggling to keep track of organizing the elements, and there was a need to arrange elements on the periodic table, and several scientists actually contributed towards the periodic table. Here on the whiteboard are just few of them. You can read on your own their contribution. The history of the periodic table, Lothar Myers, he was a German, and he was working on organizing the periodic table based on chemical properties and physical properties. Likewise, for John Newlands, he was working on the law of octave, putting 8 elements, see how they react, and every time the 8 elements show some repeating patterns. Dimitri is considered the father of the modern periodic table, and guess you see a question who is credited for the modern periodic table is a Russian chemist by the name Dmitry Mendeleev. Okay, he was looking at the atomic masses of oxide of the element, arranging from the heaviest to the lightest to the heaviest, reacting the oxygen with elements and arranging each table based on the atomic masses, not atomic number. The modern periodic table, or there was some discrepancy he could not explain. However, mostly was able to arrange or put the periodic table into the way it is right now by bombarding the nucleus and counting the number of positive charges. In this case, what we already know is that in the nucleus we have the proton. If we use atomic masses, on the periodic table, there are some elements which weigh less, but they come before those elements with less mass. In other words, a more heavier element could be in front of a less element. You can look at the argon, for example, all right, and potassium. There is some discrepancy in terms of the masses. So all these personalities contributed towards the development of the periodic table. Please distinguish them from those we looked at previously in terms of development of atomic theory and law of mass conservation, law of definite composition, and so forth. Let's see, elements are arranged in order of atomic number. This was contribution by Henry Moseley. where you bombarded the nucleus and counting the number of positive charges. Turns out that atomic number, all right, remember atomic number equals to the number of what? Number of protons, number of protons. If you know the number, atomic number, then you should know the number of protons in that element. The way the periodic table has been organized is that elements are arranged from left to right according to what we call increase in atomic number. Atomic number 1, atomic number 2, 3, so forth. We will see in few minutes the numbers, what these vertical columns, what the horizontal means, what these numbers 1, 2, 3, 4, 5. But this is just a periodic table of elements. We will also look at how the periodic table has been broken down into non-metals and metalloids. We'll come back to this in a moment. Let's see how to read the periodic table, all right? The number above chemical symbol or atomic symbol is called atomic number, which is the same as the number of protons in the nucleus of that element. This is the atomic weight, all right? It is given. You don't need to memorize atomic, you don't need to memorize atomic masses. I'll give you in the exam the periodic table. You ask is to be able to read the periodic table. You will see also such elements as carbon, that's the chemical symbol, with its atomic mass for significant figures can be more than that, and the number above it is atomic number, atomic number. Nitrogen, all right, nitrogen 14.01, this is atomic number 7 and so forth. You should be able to read. This is different from the mass number. Remember the mass number we talked about? You should be able to interpret and read the periodic table. The number above it is the atomic number. Atomic weight is always listed below. All right. Now let's break down the periodic table, organization of the periodic table. The rows on the periodic table are called horizontal. There are 7 horizontal, all right, rows. We call these periods, all right, or sometimes we call series. Periods or series are horizontal rows. There are 7 of them, and then there is what we call groups. All right, 18 vertical columns. 18 vertical columns. We call these groups, groups or families, groups or families. Call these groups or families. 2 terms associated with the 18 vertical columns. Let's see, I want to zoom this so that we can see what we call, there are 7 horizontal rows we call period or series. Vertical columns are called groups. Groups in the same or elements in the same group have similar chemical properties. That means they react the same way. I guess that's because they share similar chemical properties. We say they belong to the same family. It is important to take note of 2 systems of numbering the groups. There is the IUPAC, which uses 1 through 18. Maybe I can just minimize this numbering system. is based on International Union of Pure and Applied Chemistry. They use 1, 2, 3, all the way to 18, all the way to 18. While the American Convention, Convention use Roman, all right, Roman numeral and a letter, all right, letter A or B. For example, you will see 1A, 2A, there is 3A, all right, all the way to A. We also have the B. We also have the B. So you have to know that there are what? There are two numbering system, 1 and 2. So that here you see there is 1, 2, 3, 4, 5, 6, 7, all the way to 18 according to American, IUPAC system. An American convention, we use a number and a letter. There is the B, there is the A, there is the B and the A. Now, there is what we call the periodic law or periodicity, which states that when elements are arranged according to increase in atomic number, certain chemical properties recur or reappear or repeat itself. This is just a statement of periodicity that when elements are arranged according to increase in atomic number, certain chemical properties, physical properties keeps recurring. For example, this is group 1, lithium. This is group 1 metal sodium. This is group 1 metal potassium. If you look at group 8, this is 8A, all right, helium, neon, argon, all right, this belongs to the same group or family, which is basically the summary of periodicity, which states that when elements are arranged according to increase in atomic number, certain chemical properties keeps repeating, all right, keeps repeating. That is just a statement of periodic law or periodicity. Groups, there are certain groups with special names you need to learn. These are group 1. We call those alkali metals. And remember, when we say metals, we exclude hydrogen in group 1. We exclude hydrogen in group 1. Well, you don't need to memorize the chemicals which consist of group 1. Given the periodic table, the vertical column have all these metals. Group 2 alkaline earth metals means predominantly exist in nature as compound on the earth. Alkaline earth metals group 2A. Group 6A we call halogens, and this consists of oxygen, sulfur, selenium, tellurium, and polonium. Okay. Group 2A, beryllium, magnesium, calcium, strontium, barium, and radium. Group 7A, halogen, from the word hali, salt-forming elements consist of fluorine, chlorine, bromine, iodine, and astatine. You need to know the chemical names, all right? Should be also able to spell them. Group 8, they have special names, noble gases. They are inert, they don't react. This consists of helium, neon, argon, krypton, xenon, and radon, right? These are group A. So you will see probably in the exam or quiz, I may use these terms and you should be able to know which one is being referred to. Okay, these are 5 All right, these are 5 groups on the periodic table with special names, learn those as well so that you know. Now, let's see the periodic table also can be broken down into what we call metals, non-metals, and metalloids. Metalloids are those elements, all right, whose properties goes in between metals and non-metals. So if you look at the color coding on this side, okay, the color coding on this side, this consists of metals, except hydrogen on this end. These are non-metals. The pink, all right, or elements which lies along the staircase, along the bold zigzag. You see this? Along the bold zigzag line are metalloids. So what I'll recommend is learn those elements with the same or which are metalloid or semi-metal so that you know anything on the left side are metals except hydrogen, and then on the right side are non-metals. This consists of boron is a metalloid or semi-metal, silicon, germanium, and antimony, tellurium. Some texts they have polonium as a metalloid, but as far as we are concerned for the class text, these are the only non-metals, I mean metalloids we have to pay attention to. All right, so let's go back to our site so that at least you know now, apart from knowing the groups and periods, you should be able to break the periodic table into metals. When we say left side of the periodic table, you have to be careful with reference or with respect to this zigzag line, left side except hydrogen are metals. You should know the properties of metals, all right? They are shiny or last, all right? They are shiny. You can distinguish a plastic from a metal. They conduct heat or and electricity. Solid except mercury, all right? Most of the metals are solid at room temperature except mercury, all right? Now, non-metals are on the right side of the periodic table. With respect to the staircase, the bold zigzag, these are non-metals except hydrogen on this side, of course. Most of them, they are gases at room temperature. Most of them are gases at room temperature except few which are solid. They can be solid, liquid, for example, bromine, or gas, neon. Those are just non-metals. Metalloids or semi-metals are those which goes in between non-metals and the metals on that place. Learn, memorize until you commit to your memory what consists of metalloids. Their properties are sometimes like metals, sometimes they are non-metals. For example, hydrogen react by losing one electron, all right? React by losing one electron to form H plus. In that case, metals also react by losing what? Losing either one or more electrons. So they behave like metal in some cases. In some cases, they behave like non-metal sharing their valence electrons, So I want you to go back, make your own notes. If you haven't memorized the chemical symbols and elements on the periodic table, use index card. You can check on App Store or use any mobile device to download free programs or apps regarding the periodic table so that you do it, you learn, you commit to your memory what consists periods, or series, groups, or families. Know the elements which makes up what metals. You should be able to classify an element as a metal, metalloid, or non-metals or non-metals. That's all what I want to bring to your attention. You will see in the exam probably which one of the following is a metalloid. Which one of the following is what? Alkaline and metal or not alkaline and metal. When I use those terms, you should be able to understand what they mean. Let's move on to section 2.6 chemical formulas. And chemical formulas is basically the representation of compound when we have subscript, what they mean. For example, this is the chemical formula for carbon dioxide, all right? The subscript, you should know what the subscript means. Means we have to oxygen for every one carbon for carbon dioxide. The subscript on the right of the symbol of an element tells the number of what? Number of atoms of that element in a molecule of a compound. And remember what we say a molecule? It's the simplest unit of molecular compound consisting of two nonmetals. Molecular compounds, they are composed of the mostly non-metals. Carbon dioxide, carbon monoxide, we can have nitrogen dioxide, all right. H2O is another molecular compounds. They are made up of non-metals. And you know where non-metals are on the periodic table. Here is hydrogen gas, oxygen gas, they are the atomic water molecule, all right, hydrogen peroxide molecule, carbon monoxide, carbon dioxide, methane, and so forth. In chapter 8, we will look at the molecular models, and the chemists use color coding to represent atoms of elements. On the periodic table, oxygen, you see red spheres, oxygen white spheres, hydrogen. I had myself a model. This was ethane. I don't know if you can see my model here. This is hydrogen, the white one. And this one is carbon, the black one. Chemist uses poles, and this represent the chemical what? Chemical bond between oxygen, between carbon and hydrogen. So these are just way of representing what chemical formula, CO2, H2O. You may have elements or compound involving polyatomic ions. What does the subscript outside the parentheses mean? This means we have two oxygens, all right, two oxygens and two hydrogens. Just to interpret or show you how to interpret a chemical formula. On the periodic table, there are seven diatomic molecules. These are hydrogen gas, oxygen gas, nitrogen gas, all right. There is bromine, which is liquid. There is fluorine, which is gas. There is chlorine, which is gas. It is 7, 1, 2, 3, 4, 5, 6. There is iodine, the atomic molecule. These are hydrogen. So when you see hydrogen, in nature, they are is H2, diatomic. When you say di means two, nitrogen. Look at how you write oxygen, O2, fluorine, F2, fluorine, Cl2, bromine, Pr2. Iodine, by the way, this is liquid at room temperature, brown gas, and this is solid, all right, solid at room temperature. However, they are what? They are diatomic. Down the line, you will be required to write a balanced chemical equation where hydrogen will be involved, and in nature you should write H2. If it is oxygen, should be O2, should be O2. Let's see, there are two types of formulas. Empirical formula here, E, empirical formula, or sometimes this is E abbreviated as EF. This is represent simplest whole number, all right, number ratio of atoms, all right, in a compound. This underline the word ratio here, and simplest, the lowest number, simplest. Example is this is H2O. Simplest, the ratio here is 2 to 1. The ratio for every 2 hydrogens, there is 1 oxygen. CH4, for example, this is empirical formula. However, molecular formulas represent the exact number of atoms. Benzene, for example, C6H6, this is the molecular formula. It shows the actual number, the exact number of atoms in a compound. Now, empirical formula for this is, if I simplify that, it's just gonna be C what? CH. This is empirical formula because it represents the simplest form or the lowest whole number ratio of atoms in a compound. Nitrogen, you may be given dinitrogen tetraoxide or tetroxide. This is the molecular formula, whereas N divided by 2 is that, and this is the empirical formula for dinitrogen tetroxide. So if given the molecular formula, you should be able to write down the empirical formula for that compound. If we know the molecular compound, we can determine the empirical formula. This is the empirical molecular formula, can determine that by just dividing it or making it lowest terms. All right. Here is an example on how to write the empirical formula. So what I'll do for this is just divide. If I have P 10, all right, H 14, divide here by 2, divide here by 2. The empirical formula is P5 H7. This is the empirical formula for decadiene, the empirical formula for these compounds, just dividing it by 2 to get that. Now, pictorial molecules, this one we will look in details in chapter 8, and inorganic, if you will take organic chemistry courses, you will learn how to draw the structures of molecules. Just to highlight, the wedge represents something going away. If you look at what I'm holding on my hand, some is pointing towards me, something is pointing back towards the screen. This means here, this is going, the wedge here means going away. This means coming off the screen, and this means it's on the plane with your screen on the computer. So this is just a representation of methane using balls and stick, So that's just a representation of molecular compound structural representing that. I will not go in details into that, but we will come back again in chapter 8. Let's look at section 2.7. Section 2.7, ions. When we say ions, all right, they are charged particles, and I broke it down for you in part 1 of this lecture, what ions are. Ions, basically here, these are charged particles, and they are what? There are 3 types or categories of ions. We have cations, we have anions. This is anions right here. This is anion, and then we have polyatomic ions. We can be cations as well, or polyatomic. You see here. All right. Perhaps maybe I should move that. Yes. Polyatomic ions. We can be cation or anion. Cations are positively charged, and it's good to understand how cations are formed. Cations are formed when at least one electron is lost. Monatomic cations are formed by metals. Now, there is a pattern here. Let me just highlight how the cations are formed. If you recall the periodic table, there is 1, 2, 3, 4, 5, 6, 7, and 8 here. This is group 1. These are groups right here. Let me just make this. These are groups. What we know as far as group 8 here, noble gases, they don't react. They are stable. These are stable. They are stable elements. That means they don't react. Why? It's because, you know, their outermost shell, sorry to bring this so early, when you write the electron configuration, recall from introduction to chemistry that outermost shell, they have 8 electrons. Therefore, they do not do what? They do not lose or gain to react. Now, group 1, they have 1 valence electron. Group 2, they have 2 valence electron. Therefore, based on the group number, everybody wants to get to 8. So think of group 1, they have 1 valence electron, which means they will need 7 more to get to 8. They would rather lose that 1 electron, and the subsequent share will have 8 valence electron. So losing, because they have a long way to get to 8. Group 2, they will lose 2, and when they lose, they become positive. They become positive. So if, for example, sodium, it has 11 protons in the nucleus and 11 electrons outside the nucleus. They cancel each other. So if it loses 1, there will be 11 minus 1 electron, all right? This will mean sodium will have 11 protons and 1 or 10 electrons. You'll notice that there is an extra proton in the nucleus which is not neutralized, let's say neutralized in a way, or to cancel each other. Therefore, you will see this written as Na positive 1, Na positive 1. Likewise for group 2 metals, remember group 1 metals, hydrogen is not a metal. Therefore, even though it loses one here, most metals lose their valence electrons, means group 1 will have positive 1, group 2 will have positive 2 except for beryllium. And by the way, these are main group element. Most common group 3 is aluminum, which will form positive 3, You notice that now past 4, we are close to what? We are close to 8. So for example, oxygen in group 6 will need 2, 1, 2, therefore you will see negative 2, it will gain 2 electrons. Group 7 will gain 1 to get to 8. So anions are formed by at least an electron gaining. No, an atom gaining 1 electron. 1 electron is gained. It's not always 1, 1, 1, no. Group 2 or group 6A will gain 2 in order to make it 8. Group 7 will gain 1 to make it 8. Therefore, you will see all group 2 or group 6 will have negative 2. If it is group 5, will have negative 3, all right, for nitrogen. Of course, here we have metalloids. You're not going to see that. Tellurium, selenium, sulfur, oxygen group 2, iodine, bromine, chlorine, so forth. So understand how the cations and anions are formed. This is very important. It's going to help you down the line in writing the correct formulas for compounds, especially ionic compounds. So there is a criteria by which ions or monoatomic cations, so you should know how these are formed or what type of anion an element will form. Now for polyatomic ions here, all right, for polyatomic ions, these are group of atoms with overall charge. Here, group of atoms which act as one. All right, let's just simply with an overall charge, overall charge. This one, you cannot use the periodic table to predict their charges and how they look like. You need to learn, use index card. These include such things as sulfate. I'm gonna put that SO3 to negative. Learn their names. We call these sulfide. Learn their names. SO4 to negative sulfate. ATE. Look at the ATE and ITE, how they are being used. On nitrogen or here, NO2 with an overall charge of -1, NO3 with an overall charge of -1. We call this nitride, right? ITE and nitrate, ATE, nitrate. One last with the series, this PO3, 3 negative, and then PO4 with the 3 negative. This is phosphite, and this is phosphate. You see that? ATE. Let me stop here and then point out how the naming criteria. If you look at going back all the way here, the one with less number of oxygen in that series ends with ITE, and the one with extra or additional oxygen, greater number of oxygen in that series, it ends with ATE. Doesn't have to be 3 oxygen or 4 oxygen. No, you have to look at the series. So if I were you, If this is the first time, please use index card so that you know the difference between sulfate and what? And sulfide. If you look at this, 2 oxygen, 3 oxygen, less number of oxygen, ITE nitrite, nitrate. We have phosphate and phosphate. This is how polyatomic ions are named. Of course, there are others you need to remember. Acetate, these are common polyatomic ions. You should know how they are written. This is acetate ion. Sometimes you may see this C2, H3O2 negative, like that. It's the same thing. It's the same thing. Acetate. There is the hydroxide, right? Common one, hydroxide ion. All right. There is the CO3 with the 2 negative. You'll see that this is carbonate ion. Okay. Cn negative. This is cyanide. This is why cyanide ion. This one you need to learn. There are common polyatomic ion in the text. Learn those the chemical formulas as well as their names, naming them. Please, they are monoatomic, what we call monoatomic, which I showed you how they are how they are formed, or using the periodic table to predict them. You should as well be able to write their names. N3 negative, this is nitrite. Look at how it's written. IDA. 3 negative, this is not phosphate, phosphide. IDE, there is, and by the way, ion, you have to add ion at the end. Cl negative, this is chloride ion. F negative, this is fluoride ion. Just to give you negatively charged, there is Ca 2 positive calcium ion. T is potassium, potassium ion. Just giving you few examples. This is aluminum ion. Please learn those, naming them, writing their chemical formulas, or predicting the ionic charges from the periodic table. This is aluminum ion. Let me just briefly look at the transition metals here. If you look at this, you need to learn those common transition metals which form more than one charged particle. We use what we call Stokes system. Even though we have the old way of naming them, all right, I'll recommend you learn the new way. The Stokes system uses a Roman numeral to indicate the charge on the cation. For example, in Stokes system, there is cis, and then there is this. This is 2 ions, 2 cations formed by the same element. On the periodic table, ion number 26 can form 2 cations. In Stokes system, we call this iron 2 in Roman numeral, and then the word ion, this is iron what? This is iron 3 ion 3 ion. So the Roman numeral indicates the charge on cation. There is Cu positive 1, Cu positive 2. This is copper 1 ion. Copper 2 ion. Copper 2 ion. These are just a few transition metals and how we using the stock system. Now, there is the old way of naming them. Here, this is the one with less charge, we call it ferrous. And then this one is ferric, using OUS and IC. This is cuprous, cupric, OUSIC, cuprous, cupric, please. Those are just old way of naming them, but learn the Roman numeral, which is basically the stock system. This is stock system and how it is used in naming the cations formed by the transition metals. So here, table 2.4, common monoatomic ion, lithium, sodium ion. Look at how the Roman numeral have been used. Cuprous. By the way, this is cuprous for 1, P cuprous ferric ion. There is copper 2, which is cupric, ICE, cuprous for what? For 1 copper 1, copper 1. This is polyatomic cation, group of atom with an overall charge. Just to give you common ions, and I explained to you how the ions are formed. It's just the other uses a systematic way. That means all including polyatomic ions, the most common with overall charge of positive 1, overall charge of positive 2. You don't need to memorize the table here. I gave you how to use the periodic table to predict the ionic charges, which you should have learned in Introduction to Chemistry. This is group 2, group 2, group 2, group 2. Transition metals, you're gonna learn that. If you look at the transition metals, we use Roman numeral. I don't want you to get lost and say why sometimes we use Roman numeral, why sometimes. I don't want you to use Roman numeral for main group elements. That means the A. Only the transition metals, not all of them, form more than one charged particle, and we use the Roman numeral. Manganese, you see manganese, or US, there is positive 2, mercury 1, mercury 2, nickel 2, all right, Nicholas, there is lead 2, and by the way, there are 2, because you're gonna see this again, 2 positive plumbers, lead 2 ion, and this is like that, lead lead 4. I meant to say lead 4 here. This is positive what? Positive 4, lead 4 ion, lead 4 ion. So that's how you distinguish between these and lead 2. There is thin SN stannic, SN stannous, thin 2 ion, and then SN 4 positive, then 4 ion, then 4 ion, and then of course positive 3. The other is using the overall charge of positive 1, positive 2, positive 3. Rarely will you see positive 4. You will not see positive 4. And then we anions are negatively charged. This is the acetate ion. Please learn the polyatomic ions. I walk you through monoatomic using the periodic table: hydroxide, oxide ion, nitride ion, phosphate, phosphide, sulfate, sulfide, dichromate, chromate, carbonate, all right, permanganate. Please learn those common ions. So here, just few polyatomic ions, groups of atoms with an overall charge, okay? Learn the chemical formula and the names. I know you have those common polyatomic ions in what? In the text. I have resources on Canvas. Please, you can download, print, use those to learn common polyatomic ions. In the exam, you may be asked to identify carbonate ion. When we write the chemical formulas for compounds, which is the next thing we are going to look at, even though we look again in the next chapter, ionic compounds. All right, what's the difference between ionic compounds? There are two classes of compounds. Here we have ionic then molecular compound. Ionic compounds are generally formed between metal plus non-metal. One or metal plus polyatomic ions. Right, this is for ternary ionic compound. Before we look at molecular compound, if you look at the ionic compound, this consists of either sodium or cation plus anion, like that. Na sodium chloride, all right, sodium chloride, chlorine being green, sodium being the purple color here. This is an ionic compound, and by just looking at the chemical formula, you can state or you can classify a compound as ionic. Now, writing the correct formula for ionic compounds, you need to learn the crossover rule. Writing correct formula for ionic compound, use what we call crossover rule. Crossover rule. What does that mean? If you know the ionic charges, and then it will be easier for you to do the crossover. You see, these two is crossing over to be the subscript for nitrogen. The 3 cross over to be the subscript for magnesium. These charges you don't need to memorize, you may not see, but you have to predict from the periodic table. Group 2, positive 2, group 3, group 5, 84, negative 2. So even for sodium, all right, even for sodium chloride, if you think about it, this is positive 1 and chlorine negative 1. We do not indicate that there is positive one or negative one. I just understood that that is one is silent here, one and one is silent here. So if I have something such as magnesium and oxygen like that, you need to simplify. So this will be here, this will be here. Don't leave it as this. If you can still simplify, you can, it's allowed to do that. So the correct one actually is MgO. That is the correct formula for magnesium oxide using the crossover rule. For lead, let's say lead 4. We have lead 4 positive and 2 negative like that. If I bring down this, bring down that, this will be P. There is a 2 from oxygen, and here there is what 4 from lead. I can still divide this by 2. This will give me with PO2, and you read this as lead 4 oxide, lead 4 oxide, using the crossover rule, writing the correct formula. Suppose I want to, we are using polyatomic ion. For example, ammonium, and then for example, carbonate. How would you write that? I know somebody might think that I'm just gonna put it N4 and then 2 there, and then CO3 like that. This is wrong. You have to use parentheses. Remember, polyatomic ions, they work as if it is 1, so that this will be 2 coming from carbonate, and then there is 1. Don't just put parentheses, it's understood to be 1. You don't need to put a parenthesis. So this is the correct one. This is the correct formula for ammonium carbonate, just to show you how to use polyatomic ions. Calcium, for example, calcium and hydroxide, this will be Ca. Don't leave it like this. Don't leave it like that, thinking that you have to use the parentheses where applicable. So this will be calcium hydroxide, and that's correct formula for calcium hydroxide. That's just to give you an example on how to use the crossover rule to write the correct formula for ionic compound. You can't go wrong with the what? With the crossover rule. The key thing is remember how to predict the ionic charge using the periodic table. Learn the common polyatomic ions. It is your responsibility. Right now, it's never too late. Use index card until, or make your own notes until you know those compounds, all right? Let's see, having learned how to write the correct, all right, formulas for ionic compounds, both involving monoatomic ions or polyatomic ions. Let's see how we name them. Nomenclature here is just naming. The systemic naming or the correct way of naming compounds is called nomenclature, chemical nomenclature. We learn how to name them: ionic compound, acids, binary molecular compounds. All right, having gone through how to write the correct formulas, remember you start with what? Cation positive, followed by what? Anion negative. Likewise, in naming them, let's go to naming, all right? Ionic compounds. That. If you think of N A positive, we call this sodium. Let's look at it. Sodium ion. And Cl negative, this is chloride ion. Therefore, all right, NaCl stand for sodium chloride. If you look at what we did is just get rid of that to form sodium chloride. So if you know how to name the cation and an ion, you should be able to write, and you start by naming the cation. Cation goes in fast. Cation goes in fast. Look at calcium. This is ion, and then the hydroxide, hydroxide ion. So that Ca in parentheses to here. Calcium, what this is calcium hydroxide, like that. I got rid of what? I got rid of ion. So if you know how to name the cation, anion, or polyatomic ions, naming ionic compound is pretty straightforward. Now there are those ions which form more than one charged particle. For example, how will you name these two compounds? And if you look at the first one here, all right, this first one here, there is iron. You have to know that this is iron 2 ion, and then there is OH negative. This is hydroxide, all right, hydroxide ion. There is hydroxide ion. There is ion 2 ion. So a proper way of naming this is ion ion 2 ion. Look at how parentheses. I've seen students just saying ion. Look at this. They don't know what is wrong with it. Ion. This is ion 2. I meant to say ion 2 hydroxide, ion 2 hydroxide. Yes, students say iron hydroxide like that. You see, this is more tempting to say. This is wrong because you didn't indicate. If that's you, you didn't indicate the charge on cation. You need to indicate that. Having gone through that, so you should see this. This has F3 positive, and this is ion 3 ion, and then OH negative. This is hydroxide ion. Therefore, this guy is ion 3 hydroxide, ion 3 hydroxide. So I'm just gonna have that ion 3 hydroxide. That's how you name the ionic compounds formed by transition metals which form more than one charged particle. Use the Roman numeral, the stock system. Even though you may see sometimes the old way of saying ferric hydroxide or ferrous hydroxide. There is copper 2 sulfate like this, CuSO4. Remember, sulfate is positive negative 2. There are two cation formed pi. This is negative positive 1, by the way. There are two cation formed by copper, either positive 2 or positive 1. But from this chemical formula, I don't see 2 coming down here. Remember the crossover rule from sulfate. So I know I'm dealing with copper 2. And the proper way of naming this is copper 2 sulfate, copper 2 sulfate. Let's just give you a few examples on how to name ionic compound, So inorganic compounds, those compounds which consist mainly of metals other than other than the element carbon. If polyatomic cation ends with IUM, all right, we change or we use the Roman numeral 8. Fernandez, I've shown you how to use that. If an ion is an element, changing the ending IDE to is ending to IDE. I've shown you how that works. These are just few polyatomic ions, and there is a way, all right, learn this, involve, know which one you are dealing with, so that you name them. Here is an example, sulfate. Look at sulfate. Sulfate, so ATE, there is the sulfide. If it was this, if it was CuSO3, and then this one is copper 2 sulfide. Likewise, if ending with ATE, you need to know those. I've given you example on how to name polyatomic ions. Please read those and make your own notes. This is just naming of polyatomic ions. Let's see, how do we name acids? I'm done with the here. I'm done with the ionic compounds. Please see me. If you need more assistance, use the SI session to read more or seek more remedial work on naming compound. Let's see, acids. Acids. There are two types of acids. We have what we call binary acid, and then there is oxy acids. All right. Binary, from the word binary. All right. This means they have two compounds, HF and then aqueous. And by the way, we indicate AQ as the physical state, HCl, aqueous, HBr, aqueous, HI, aqueous, binary acid. How do we name them? It is easier to name the binary acids. Binary. Okay, I'm gonna have binary what? Binary acids, and this is HCl, for example, AQ. This is hydrochloric. See how we change the ending to IDE, and then the word acid here, the word acid, hydrochloric acid. Acid must be dissolved. Aqueous means dissolved in H2O. All these they are dissolved in H2O means AQ. HF and then aqueous. This is hydrofluoric acid. And then there is I, and then this is iodic acid. Look at how the ending I acid, and then the word hydro. For binary, we use hydro, okay? We use hydro so that you know how this has been named: hydrochloric acid, hydrochromic acid, hydroiodic acid, HPR, hydroiodic acid, we use those. Now, for oxy acids, this portion of this one, they must have oxygen, they must have hydrogen, they must have AQ. These are the signature things I'm looking. There is polyatomic ion here, polyatomic ion involved in the acid. There is a systematic way here, oxy acids. We use polyatomic ions to determine how we change the ending to OUS, OUS. For example, all right, here, HNO2 and then aqueous. And then there is HNO3 and then there is aqueous. Aqueous. If you look at the polyatomic anion, this means polyatomic ion, we have NO2 negative. This is nitrite, ITE, and then 3 negative. This is nitrate, ATE. So if ITE is the ending for polyatomic ions, we use OUS and then the word acid. So this is how you will name this. This is nitric acid. No, nitrous, OUS. This is nitrous. All right. This is nitrous acid. And then this is nitric acid. We have nitric acid. We're gonna have that nitric acid. Pay attention to ATE, ITE. This goes back to polyatomic ion. If you did not, or if you fail to nail down naming polyatomic ions, the problem will compound in naming of oxy acid. That means of acid with what? Polyatomic ions. All right. So that if I have H2SO3 and then aqueous and then H2SO4, this has sulfide and sulfate polyatomic ion, and the systematic way of naming this is sulfurous and then acid. I'm changing to OUS, and then this one is sulfuric acid, sulfuric acid. And by the way, this is aqueous. You must have AQ, means dissolved in H2O, in H2O. I'll go back to end of chapter problems, see how you name, practice how to name the oxy acid, as well as binary acid. Remember, there are two oxy acids with polyatomic ion is involved in naming them or in writing their correct chemical formulas. and only those with hydrogen and non-metal and aqueous, of course. Now, let's see, Paul, molecular compound. When we say molecular compound, all right, molecular compounds are compounds made up of non-metals, non-metals, all right? And binary means two. Binary means two. If you look at table 2.6 in the text, these are prefixes used to indicate how many atoms are in the compound. You need to learn what these terms means. Mono means one, di means two, tri means four, tetra means, tri means three, tetra means four, penta five, hexa, hepta, octa, nona, deca. We have even more than that. We have more than 10, but for our course, we'll only have to learn the first 10. Note that the prefix mono is used to denote the number of atoms of each element in a compound. Mono is not used on the first element listed, all right? We don't use that. For example, here, to show you, this is the deadly gas. We call this carbon what? If you look at this, carbon monoxide. Carbon monoxide means there is only one oxygen. This mono is not used in the first. You cannot say mono carbon monoxide. We don't use in the first. Look at this. This one CO2, common gas. You know this. This is carbon what? Carbon dioxide. Carbon dioxide means two oxygen. We don't use monocarbon dioxide, monocarbon dioxide. So please note how the prefixes are used. SF6 sulfur, hexa, fluoride. We treat the second element as if it is anion ending IDE, not hexafluorine. No. You treat the second element as if it is anion IDE, IDE. For 2O4 dinitrogen, this is dinitrogen tetroxide. Sometimes we have tetroxide for two. So penta, hepta, and so forth. Learn how this has been used. Carbon dioxide for two, carbon tetrachloride, and so for dinitrogen pentoxide, carbon monoxide. All right. Some others, if you notice here, some texts they omit O if there is a vowel following. You see this? If a prefix ends with A, that is tetra, and then O, name of the elements begin with the vowel, the two successors are often edited into nitrogen pentoxide. So I'm just gonna get rid of this to make sure that we get it right. I don't want you to miss in online homework. This is dinitrogen tetroxide. We use, if they are following, we use, you remove the first vowel in the second element and just give that. What that means is for this tetra, penta, hexa, hepta, all those and what is following start with A, change that to ending. Well, I'm not going to require you learn the